So I want to finish the class by taking the themes that we've talked about all semester and sort of running them up to the present day. This is an idea based on an essay by Rainer Banham called Stocktaking that he wrote in the early 1960s, where he argued that the field of architecture was being slowly overtaken by various engineering disciplines, structural, mechanical, cladding engineering in particular. And it was intended as a sort of like, where are we now? Where's the field going? How has it changed? And what should we be concerned about going forward? So this is a little bit like that, just 60 years later, looking both at the problems that the field of construction faces and also the opportunities that we have with new tools, new materials, things like that. And I want to finish also by going back to some of the philosophical discussions we talked about in the 19th century to ask some questions about where we stand, not just in terms of how well optimized or how well suited the field is to these problems, but also what some of the larger moral, ethical questions are about where we stand. So to begin with, I would argue that the thing that probably affects us more than anything else is the switch from thinking about construction and architecture as predominantly concerned with bigger and better structures and more concerned with thinking about how we fit into a changing environment. We talked about the history of sustainability in the last lecture, and this has only, of course, grown more and more urgent as time has gone on. We are now facing really a species level problem in what we've done to the environment, particularly to the atmosphere, and what the implications are for us as a species, but also for us as a civilization. We know that we're on track to a warming planet that will change irrevocably the climate and therefore the weather that we deal with. Parts of the globe that we've assumed are habitable may become uninhabitable, and vice versa. This is a problem that has been noted not just by climate scientists, but increasingly by businesses and governments as well. To me, maybe the most notable moment was in the mid-2010s, when insurance industries began realizing that their business models were going to change drastically with the onset of climate change, that they were paying out more and more for these large-scale climate disasters. And in fact, there is this fight between insurance companies and energy companies over what really needs to be done and how urgent that is. Today, I think there's broad agreement that this is a problem that needs to be addressed in all sectors, but construction is one of the largest contributors to global carbon dioxide emissions, has been for years, and therefore we have a particular both responsibility, but we also have a particular opportunity to make a really big impact in solving this species level problem. Building operations, energizing our buildings, heating and cooling them and lighting them, takes up nearly a third of carbon emissions, 27%. And when you add the embodied energy, the embodied carbon that goes into constructing buildings from cement, iron, steel, and aluminum, but also from building the infrastructure necessary to make buildings go, what you find is that the built environment contributes about 42% of carbon dioxide emissions to the planet. And therefore, we have the biggest share of the problem, the biggest responsibility for the problem. But if we change the way that we work, we also potentially have the biggest impact on it. The good news out of this is that we have a variety of tools, new tools that seem like they're going to maybe give us some leverage in actually addressing these. About 10 years ago, in 2013, the AIA commissioned the consulting firm McKinsey to look at what technologies were likely to be the most disruptive by 2025. And we're now on the doorstep of 2025, so we can sort of look at this and assess exactly how well McKinsey did. But the idea was to think about what the tools, what we'd have in our toolbox as architects, but also as builders, as engineers, that would change the profession, right? That would change or disrupt the way we build buildings. And McKinsey thought that most importantly was probably mobile internet. And I would say that some of that has certainly come true. We are more used to working on our phones or on iPads, on job sites, in remote locations than we ever have been. Whether that's been the biggest disruptor or not, though, I think is up for grabs. And it's worth looking at some of these other technologies and thinking about how they've changed the way that we practice, the way that we build. Probably the most impactful, and one that McKinsey recognized would be one of the most impactful, was the automation of what we do, handing over a lot of the sort of drudgery work, if you like, of designing and constructing buildings to digital technologies. This idea goes back 50 or 60 years to the very, very early days of cybernetics. Doug Engelbart, who was one of the pioneering thinkers of cybernetics, picked architecture as one of the professions that would potentially benefit, or at least be changed the most, by the advent of digital technologies. This description from 1962 is not entirely inaccurate in terms of what CAD has allowed us to do. We, the architects, sit and enter a series of specs and data. He didn't foresee the mouse or the sort of graphic interfaces that we have. But his idea was that we could type in the specifications for various pieces of the building, the depth of the slab, the width of the concrete walls, the height of all the elements, etc. Once we type that in, he says, then the computer thinks about it for a bit, gives us a visual of what that would look like. And interestingly, he understands that those elements are all connected. They're all lists that can be referenced to one another to give us basically a three-dimensional spreadsheet of what we're building. And I would argue that this has come largely true, that when we work with Revit or another building information modeling technology, we're essentially working in a large spreadsheet with a graphic interface. And BIM, Autodesk, Revit, and programs that are similar to that allow us to not only see what the end result is going to be, it allows us to coordinate things like systems and structures, and in practice allows us to keep track of those, right? It lets us take off quantities much more easily and lets us model the building in multiple ways. So we can do cost takeoffs, but we can also model the structural behavior or look for conflicts between services, things like that. This has been a profound change just in the last 25 years. It has eliminated an awful lot of the sort of checking work, a lot of the clerical work that went along with practice, even as late as the 1990s. And of course, this is spread to all sorts of other subdisciplines. We can select furniture, we can see if the furniture fits, we can place the order for furniture, we can get a spreadsheet of all the furniture that's going into the building, really right out of the box that we have on our desks. That has changed, that has streamlined an awful lot of what we do as designers. It's given us a lot more time that in general we've tended to give right back to the clients, right? That we've become a more efficient profession, but that efficiency largely has benefited the clients that we serve rather than transforming maybe the way that we work. This idea has been, or the larger implications of this idea has been speculated on by a lot of folks, notably Randy Deutsch, a colleague here at the University of Illinois, who in discussing the data-driven basis of design going forward in 2015 talked with a partner at LMN Architects in Seattle who foresaw architects becoming what he called data hackers, right? Thinking about the building as a big set of code and being able to get into the code of the building and actually sort of transform not just what it is we build, but also how we build it. What do we mean by that? Well, I think that one of the first examples you can see of this is the parametric design that went into some actually fairly early high-tech projects around the turn of the millennium. The so-called Gherkin, the Swiss Re Tower by Foster and Partners that was built between 1999 and 2003, did this. It essentially turned the building into a set of geometric codes and allowed the designers to adjust the kind of geometry net of the building to find the most efficient set of floor plates. This is also used to model the building in aerodynamic simulations. You can see from the graphics that this is clearly 25-year-old digital technology, but it really was one of the first instances that I can find of the code of the building, in this case the diagrid geometry that basically governed all of the structure, all of the cladding, but also all of the floor plates, the code of the building really being manipulated by designers, right? Taking the building and understanding how to kind of hack the data that goes into it to create a design tool. That sort of ability very quickly trickled down to the point where this is a student project using Grasshopper from 10 years ago, where you can see that sight lines and acoustic lines are all being played around with by what Sam Miller would have called the DNA of the building, right? Shaping the space, running sort of simulations on it and looking to see what comes back, being able to very quickly manipulate the code on the left to change the form of the auditorium on the right. This has often been incorporated with more feedback. So Kieran Timberlake were pioneers in thinking about ways to both wire buildings for data collection and then to turn around and use that data collection to think about how to better adapt the building to its climate. So this is an app that Kieran Timberlake designed for Revit. That's designed to take the building's performance, to measure how warm things are, how cool things are, how air is moving through the building, and to think about how to maybe better manipulate the cladding of the building to relate to its environment. This can happen on a more sophisticated scale too. We get a data-driven design that lets us see what the impact of solar gain is on building structures. Cove Tool was one of the early examples of this. And also very desktop-based computational flow dynamics. One of the most complicated of the sort of 80s and 90s digital applications very quickly in the 2000s became something that was desktop-based and lets us see not only what the sun can do, but also what the prevailing winds would do, right? What the various effects of wind and rain are on buildings that we design as well. The fact that this has come down from sort of $1 million applications to desktop software has given us the opportunity to be much more agile, both in collecting data, but also thinking about how that data can influence or support design decisions that we make at the table. We've also seen technologies that have enabled us to very quickly iterate or come up with very rapid new ideas that build on one another and that gradually sort of learn from the process. Galapagos and Grasshopper, both ways of very quickly coming up with different design scenarios. Galapagos is a so-called genetic algorithm that throws a bunch of variables at a given setup, looks at the results to see which ones perform better, and then sort of dives deeply into those to try to figure out if there are spaces in between those examples that might even be better and better, right? Might be more and more optimized. This sort of genetic algorithm can get applied to structures in particular, and it's been used over the last 15 or 20 years to really look at optimizing large-scale structures, long span and high-rises in particular. Here's a paper from a group at the University of Michigan that's looking at different ways to structure both long spans and tall buildings. And the genetic algorithm looks at hundreds and hundreds of iterations, begins to see patterns where things get more and more efficient, and then offers variations, random variations within that design space to see if there are even more efficient options within that. So it's a way of, in this case, reducing the weight of a structure for a given set of performance parameters. In the last couple of years, of course, we've seen the rise of artificial intelligence, and this is basically taking something like Galapagos and supercharging it. So IBM's Watson program was designed as a very, very large-scale data mining project that would very, very rapidly go through thousands and thousands of iterations. One of the applications early on was to look at real estate values in big cities and to try to understand where there might be opportunities for investment. But this also has trickled down into architecture. We've seen this huge burst of artificial intelligence software, but also web-based AI that lets us visualize and maybe at some point will actually let us get in and design things like structures that again, we're giving over a lot of our sort of intelligent labor that we do as architects being handed over to digital technologies. Thus far, I would argue that the role of AI has been sort of gimmicky. And what we've seen more than anything else is the production of images, which are impressive but relatively simple compared with the sort of integrative work that we tend to do as designers. One way to think about this is to think about what we do that isn't replicable by artificial intelligence. About 10 years ago, NPR did a study of how jobs might be affected by artificial intelligence, which then was still sort of on the horizon. And they had this little website that you could sort of plug in what you did for a living, and you could see whether you were likely to get put out of work by a computer or not. Interestingly, if you put in architectural and civil drafters, so people who work preparing drawings but maybe aren't necessarily licensed architects or engineers, the bot thought that you had about a 52% chance of your work being automated. And when we look at technologies like Revit and the automation that already goes on within that sort of software, that seems pretty conservative, actually. There's a lot of work that we used to do by hand that now gets done not only digitally, but also sort of with artificial intelligence, rudimentary though it might be. Interestingly, though, when Planet Money changed the parameters a little bit, and if you put in that you were actually an architect instead of just a draftsperson, you have almost no chance of being replaced by a machine. And that's because artificial intelligence is very good with data-heavy problems, solving things like what's the most efficient way to lay out ducts in a building while avoiding conflicts. But it's not so good, for instance, at running a meeting or interviewing clients to find out what they really need. Or to come up with clever solutions that maybe aren't part of the optimization space that something like Galapagos looks at. We also negotiate. We have to think about not only the cost of things or the efficiency of things, but the value of things, something we'll return to at the end of this particular lecture. So the difference between a draftsperson and an architect is really the difference between a job that can be done by some of these new AI technologies and a job that really does require us to be human, to be actually engaged as a thinking kind of agile mind instead of just a data cruncher. And just as an exercise, right, here's an expert opinion that says AI is unlikely to put architects out of work entirely. It will change the way we work. It'll help us generate designs. It'll help create drawings, which might, like the promise of Revit, increase efficiency and reduce errors, maybe free us up to focus on more creative aspects of the work, or give our clients better service for less time and therefore less fees. But it's those unique skills and expertise like creativity, critical thinking, and the negotiations that we do with human beings that are likely to keep architecture in the realm of like actual people. The expert who comes up with all this is, of course, an artificial intelligence itself, right? This is ChatGPT's answer to the question of whether it's going to replace architects or not. Other tools that McKinsey was looking at that I think have really exceeded the potential that they saw are something called the Internet of Things that we'll talk about here in a minute, and then a lot of questions about energy and about materials. So energy storage, 3D printing, and advances in materials, McKinsey thought were relatively unimportant, and I would argue that those have actually been much more important than you would have thought 10 years ago. McKinsey thought autonomous vehicles would be relatively important. I think that is a bridge that we haven't really yet crossed. Those still seem to be quite problematic in their applications. And finally, McKinsey did not think renewable energy would be important, and yet I would argue that maybe has been one of the most significant technologies that's come in, maybe not disrupted so much the practice of architecture on the ground, but it's certainly changed the way that we think about energy and energy consumption. One example of this is the state of Iowa, which we don't think of as a particularly maybe technologically advanced state, but in fact, over the last 10 years, Iowa has been one of the leaders in renewable energy, in large part because it has access to so much potential wind power. You can see from the statistics on the right that by 2021, the state was generating more than half of its energy from wind power. And in fact, in 2023, they had their first day where 100% of the state's energy was generated by wind. This, I think, maybe it's not a disruptive technology in that it doesn't change the way designers think at the desk. But if you think about the impact of this on that, the 27% or so of carbon emissions that are based on running buildings, this really is significant. And the more that we can look to renewable energy to power our buildings, the more readily we'll be able to address some of those CO2 problems. The use of renewable energy requires a couple things. It requires a great amount of space. So we're seeing, for instance, the use of rooftop solar come into play. In a lot of cases, you can lease the solar panels and sell the energy to a local utility. And we're seeing a lot of work on storage. Right, you want to turn the lights on not just when it's windy out, but also when it's not windy out or when the sun's not shining. And so how you take that generated electricity and store it is something that remains a really big issue, and potentially something that we as architects have to look at going forward, right? Space for fairly large batteries to power our buildings when the wind and sun aren't out. This is one example of one of these ventures that's looking to put rooftop solar wherever it can. And they will come out, they will install the panels, and for relatively low cost, they will then lease the panels and sell the energy to the local utility. It's a way that the homeowner can kind of reduce their energy bills while contributing to the overall acceptance of renewable energy. And as Bill McKibben, one of the sort of leading thinkers of the sustainability movement, has said, you know, if you really want to change the world right now, instead of being an architect, you should go be an electrician, because one of the bottlenecks to getting enough renewable energy into the grid is that there aren't enough people right now available to install all the solar panels we're going to need. So here's a renewable technology that is disruptive, again, maybe not right at the desk, but in the way that everything surrounding how we build proceeds. We'll look at a few other examples of these disruptive technologies in the second part, the new tools that we have to work with. Including some of the things that McKinsey has talked about, but also developments in materials, and maybe more importantly in processes, how we make the materials that go into the buildings on the job site.